And our project is 2ndVision, a smart navigation suit to ensure safe movements for visually impaired using machine learning and IoT. So the introduction is, in response to the challenges faced by blind and visually impaired, exacerbated by the increased prevalence of screen-related visual impairments, this proposal aims to address the shortcomings of existing solutions. The proposed solution consists of a cost-effective and secure approach, featuring a suit equipped with sensor and motors complemented by a mobile app. This integrated system enhances the navigational experience for the visually impaired, offering key features such as traversal in any environment, map-guided navigation, and timely warnings of high-speed dangers. The suit utilizes the time-of-flight sensor and vibration motors to convey crucial information to users. And one second. The growing epidemic of myopia due to increased screen is leading to more cases of serious visual impairments, including macular degeneration and retinal detachment. With this epidemic of blindness, particularly impacting the younger generation, novel solutions must be developed utilizing more up-to-date technological advancements beyond conventional options like guide dogs and walking sticks. And of course, a large targeted customer is the visually impaired actual blind people. However, the high cost and unreliability of current solutions globally discourage officials and policymakers from making necessary enhancements for the blind and visually impaired. For example, assistive reading technology only helps in cases where words need to be distinguished and cannot help in navigation and environment nor offer warning in dangerous situations. Wearable objects, on the other hand, detection devices work well in identifying what is in front of the user, but they cannot give accurate assessments of the distance away someone is from obstacles, nor can they offer quick enough warning in dangerous situations. Both solutions listed only cost a lot by, which cannot be afforded for most of the people, since a guide dog, I believe, is $50,000 annually. And to tackle the problem of high cost, inconvenience, and safety risk preventing current solutions, our proposed approach seeks to provide a cost-effective method for achieving three interconnected navigation objects for the visually impaired and blind: traversability, map navigation, and emergency warning detection. With these solutions, user can experience unparalleled safety, convenience, and unreliability, and at an affordable cost. And we did some research about Kyushu University Haptic Vest. It employs 60 actuators for tactile navigation, providing only directional cues through torso vibrations. However, its sensory scope is narrower than the 2ndVision project, which we're doing right now, which incorporates a lidar and auditory signals, offering a more interactive and comprehensive navigation aid for the visually impaired. The smart canes based on IoT enhances traditional white canes with location and obstacles detection, but is limited by sound feedback, especially in noisy environments. In contrast, our project, 2ndVision, overcomes these limitations with advanced sensors and a multi-model feedback system, along with an app integration for comprehensive functionality. And the proposed solution involves smart glasses with a Raspberry Pi and a camera model, utilizing sonar sensors and deep learning for obstacle and identifications, OCR for text reading, and voice commands for user interaction, providing a versatile and adaptive solution. And our solution addresses the growing visual impairments by introducing a cost-effective approach that combines a wearable suit. And let me just turn to here. So this is basically a diagram of our suit. And this suit integrates a camera and 10 lidar-based time-of-flight sensors strategically positioned to detect obstacles in all directions by measuring the returning time of emitted light pulses. These sensors, coupled with vibration motors, convey visual information through distinct patterns for navigation, object alerts, and obstacle warnings. The blind accessible app, developed using Flutter UI development kit and the Dart language, complements the suit with object detection and text-to-speech features. It utilizes Map API like Google Maps and send directional information. And our solution excels in providing three interconnected navigation for the visually impaired: traversability, map navigation, emergency warning detection. It's all featured in the lidar detection. Its cost-effectiveness arises from leveraging modern technologies and innovative fusion of hardware and software components. In contrast to expensive and limited functionality existing solutions, our approach ensures unparalleled safety, convenience, and reliability at an affordable cost. And basically, we had multiple challenges to do this suit, and one of them is implementing research proposal, object detection, and creating a simple app for interfaces. Object detection, since we're using an AI model for deep learning, and it's very time consuming as the last project is. And we have a bad training model and not enough training data, so the outcome of our project detection is an ineffective system that cannot detect certain traffic signs properly. However, if we were to switch to an image data set that contains traffic signs specifically, our model will possibly be better at recognizing the things that we wanted to recognize. And of course, for the visually impaired, it's very hard to create an accessible app user interfaces. We have to survey a lot of people and see which one is the most comfortable UI for them. And to the solutions. So our solution consists of a wearable suit and a blind accessible mobile app. The suit designed to hold the phone in the front pocket, like the last diagram have showcased, integrates a camera and 10 time-of-flight sensors using lidar technology. The suit will have 10 flight sensors placed on every side of the user that detects distance through light detection and ranging lidar technology that times the return time of emitted light pulses. And so here we have a little map. This map navigation display for debugging purposes. In practice, directions will be sent to the suit via Bluetooth. So if you're navigating through places, it will send the direction you'll be going through this map and via Bluetooth, of course. And here we have an object detection of exterior items and interior items. So even if visually impaired, they will be recognized these items without even touching them. And the model we created is being used to predict images from the information from the phone camera. Phone camera height and width are specifically, and we signal position detection if objects have an intersection over the unit threshold of more than 0.3. Resulting predictions, object detection is then sent to the result callback method to be formed into boxes around identifications. And so here's the main part, our suit. And to address this figure is basically a diagram of our suit from front view, back view, and cross-sectional view. And here is the overview of the functionality of 2ndVision suit. Object detection danger. It's kind of hard to see, but so how this works is basically the closer you get to an object, the harder the corresponding radar and motor will vibrate. So it's basically transferring this 3D world, which the visually impaired cannot see, to a 2D world that will be transformed onto the user's body. And so, for example, if you hold like an apple in front of you, the user will feel the apple or an object in there just vibrating at the exact location. And deep learning models. And the code displayed controls the front motor's vibration frequency based on the reading from its paired sensors. The front, sorry, the front sensor readings update every 100 milliseconds, and the if ladder below categorizes the reading into different ranges of its max detection distance and tells the vibration motor to play waveforms of specific vibration intensities based on which range distance reading is. Specifically, for each 25% decrease in the distance from the max detection range, the vibration motor switches to an increasing intense vibration. And this will be like the key feature as I've just said earlier, that the closer you get to an object, the harder it vibrates, basically transferring the 3D world to another 3D map on the body, a tactile map. And going back to the core features, as you guys can see, this is basically a whole layout, and we have a physical suit. And it have a 360 haptic map navigation as it's in the phone, and safe traversal in any environment as the guide dogs and the canes cannot provide. Guide dogs, of course, being $50,000 annually is very not cost effective. And canes, on the other hand, sometimes limited to a short range and only provides a small range of like maybe 1 meter in radius. And timely warnings of high-speed dangers, of course, if we're going through traffic, our suit can detect maybe if a car is going by really fast, and it provides immediate alerts for potential high-speed dangers, enhancing user safety with timely warnings. And of course, the most important, traffic sign detection. So basically, if you want to cross the traffic, a guide dog will see if there's any pedestrian crossing by, but with our suit, the app will say, if this is green light, then it'll say it's green light, so the user can move. Entirely replaces the guide dog feature. And we did many experiments. To prove the effectiveness of our solution, we devised an experiment to evaluate the effectiveness of our suit's object avoiding capabilities. We used a validation experiment for the object avoidance of the suit by constructing a simple maze made of cardboard spots of varying heights and letting blindfolders testers walk through the maze. Three different groups of blindfolded testers participate in this experiment. A group that wears the suit to navigate through the maze, a group that wears the suit to navigate through the maze, a group that uses a walking stick to navigate through the maze, and a control group that has no assistance. We measured the amount of times that each group bumped into a cardboard walls of the terrain and the time each participant took to complete the maze. We then graphed the bump data for each group on the distribution graph and the average time and the time. So here we can see the graph, and this is distribution of bumps of participants for control group, distribution of bumps. So this is basically us comparing like our suit to the original idea, and our suit is basically very effective. And I have a video to show. So this isn't the experiment video we did. This is just like proving our suit's capabilities. And I'm just walking here blindfolded, of course, wearing the suit. And I'm not even walking fearfully. I'm not like trying to see if there's anything in front. I've not, of course, blindfolded. I can dodge children's sensors. A few sensors placed on the lower back, placed at the 45-degree angles. Here I can walk swiftly. And this is, yeah. The closer I look, I walk to something, the harder it vibrates. And this is basically showcasing the suit's capabilities. Of course, it's not in the experiment. This is just a little video. And this bump distribution here showed a clear advantage for VEST thanks to the immediate signaling of the vibration motors, with the control group having an average of 4 bumps. The VEST performance of almost 0 bumps shows a significant relative increase in blind person's ability to avoid obstacles. Canes also perform solidly in avoiding bumping into walls, which is justified by the cane's ability. However, the advantages of the canes, when we factor in the time in which a tester can complete a maze, although canes are great at searching for objects in their near vicinity, it's too slow when compared to the VEST, which requires no action on the side of the user to detect objects. This distinction allows VEST testers to walk through the maze without constantly tapping for obstacles, greatly decreasing time they spend on the maze. Our data further justifies our conclusion that the VEST performs better at object avoidance. Existing solutions, the average time spent on the maze of VEST testers is on average 16.76% higher than the cane users and is approximately 40% higher than the control group. Not only do we have to guarantee the effectiveness of the suit, the most salient feature of our app should also be tested. Namely, we want to make sure our emergency notifications work in a real-world scenario, giving the user enough time to react. We used a verification experiment for the danger warning experiment. There'll be no testers involved with this experiment. We will place a suit with the object detection feature on the app, open a dummy doll, and use a tennis ball machine to throw a high-speed ball at the suit. And here is the result of this experiment. This allows us to measure the amount of time the user has to avoid danger, so we can probably verify the effectiveness of our object detection. And this graph is basically a graph of time gap of 30 trials and overall average time gap. The average time gap between the motor vibration and impact of tennis ball is around 3.22 seconds, which gives the user a short yet not impossible period to react to an emergency warning, as human reaction time is around 0.2 seconds, such as dodging any incoming speeding vehicle or stopping at a red light. Given that human reaction time is faster with touch stimuli, such as our vibration motors, the user has a little over 3 full seconds to make a response after sensing a vibration. That's a lot of time. Even in the most extreme scenarios in our testing, where the time gap is only 2.5 seconds, the user still has over 2 seconds to avoid danger, which guide dogs and, of course, canes can impossibly do. They can't do it. And our conclusion, our approach is limited to the battery life of our suit. If the suit runs out of battery, all features will cease to function, which can be detrimental if it happens at the wrong time during the day. We plan to either add larger batteries for the suit or give plenty of low battery warning so the user knows to recharge the battery, or even giving the suit multiple batteries. So if the suit even runs out, we can replace the batteries. Additionally, through our suit of object avoidance satisfactory, we will strive to increase the time gap of notifications before a dangerous event occurs, Although 2.3 seconds of response time is relatively long, we have to consider all possibility of human error, as it's very likely that real user will freeze in shock or fear and waste the time gap provided by the notification. Although we have referred to this project as a solution or a tool, this is more than innovation. It's a commitment to the holistic well-being of the visually impaired and blind community. With this suit, we turn darkness into a landscape of tactile awareness, where every touch illuminates a path forward. And thank you. That's my presentation.